3I Atlas. First glimpse after the Sun. The distance is 29 million kilometers. The date is March 15, 2025. The instrument is the James Webb Space Telescope, tracking through its mid-infrared array, locked onto a coordinate that has been dark for 6 months, hidden behind the solar disk, invisible to every observatory on Earth and in orbit. The object is catalogued as 3I Atlas, the third confirmed interstellar visitor, a traveller from beyond the boundary of our Sun's influence, moving through the inner solar system on a trajectory that should have been predictable, calculable, written in the language of gravity and momentum. But when the Webb's sensors reacquire the signal, something is wrong. The albedo, the measure of how much light reflects from its surface, peaks not in the dust grey of stone, not in the ice white of frozen volatiles, but in cobalt blue, a colour that doesn't belong to comets, a colour that suggests composition, structure, chemistry that defies the models. The analysts call it a data glitch. The astronomers call it 3I Atlas, re-emerging from solar occultation. And now, for the first time since it passed behind the Sun, we can see it again. But something has changed. The polarization signature, the way light bends and twists as it bounces off the surface, has shifted. The rotation curve, the gentle tumble that all natural bodies exhibit, has altered. Even the faint radio echo, detected weeks ago and dismissed as instrument noise, has returned stronger. The clock is running. In 19 days, 3I Atlas will slip beyond the Webb's line of sight, entering a region of space we won't be able to observe again for decades. The geometry of orbits, the limitations of our instruments, the slow dance of Earth and object and Sun, all conspire to give us one narrow window, one chance. And then there's the oddity that no one can explain. A spectral dip at 21.3 centimeters, the same wavelength used by hydrogen mapping, the same wavelength proposed decades ago as the universal frequency for interstellar communication. The probability that this is coincidence has been calculated. It sits at 1 in 800, low probability, high impact. Before we go deeper, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding. Because what happens next may rewrite what we thought we knew about the universe, about ourselves, about whether we've ever truly been alone. The silence is ending. The data is arriving. And somewhere between the calm of scientific observation and the urgency of a closing window, we stand at the edge of something we don't yet have words for. This is not science fiction. This is March 2025. Where sunlight fades and mysteries wake, this is Beyond the Solar Veil. Chapter 1, March 15th, Reacquiring the Stranger. The first signal arrives at 0317 UTC, Deep Space Network Station. 43 in Canberra, Australia, receives the packet from the James Webb Space Telescope, a stream of infrared data compressed and encoded transmitted across 1.5 million kilometers from the L2 Lagrange point where Webb orbits in perpetual balance between Earth and Sun. The data is tagged with the tracking ID for 3I Atlas. The object that hasn't been visible since September of the previous year, when it passed within 42 million kilometers of the Sun and disappeared into the glare, swallowed by the light of the star that gives us life and blinds our instruments in equal measure. For 6 months the object has been a ghost, a mathematical projection, a dot on a chart extrapolated from the trajectory it held before occultation, calculated using the laws of gravity that have governed celestial mechanics since Newton first put pen to paper. But gravity, as it turns out, is not the only force at work. The position recorded by the Webb is off by 0.002 degrees, a tiny deviation, a fraction of the Moon's width as seen from Earth. But at this distance, that deviation translates to nearly 200 kilometers, a displacement that should not exist if the object were following a purely ballistic path. The first analyst to notice is Dr. Elena Revas, a researcher at the European Space Agency's Operations Center in Darmstadt, Germany. She's been awake for 19 hours, monitoring the Webb's tracking schedule, waiting for this exact moment. She sees the coordinate mismatch and assumes instrument error. She runs the calibration check. The Webb's gyroscopes are nominal. The star trackers are locked. The pointing accuracy is within tolerances. She runs the trajectory model again. The deviation remains. She sends a message to the NASA Goddard Space Flight Center, flagged urgent, with a single line in the subject field. 3i position anomaly, request verification. Within 40 minutes, 3 independent teams confirm the same result. The object is not where it should be, and the deviation is not random. It follows a vector, a direction of motion that suggests acceleration, however slight, in a direction that cannot be explained by solar radiation pressure alone. By 06 Zayu UTC, the term non-gravitational force appears in the first internal memo. By 8 Zayu UTC, the term outgassing is proposed as the most likely explanation. Comets do this. As they approach the Sun, frozen volatiles sublimate, turning directly from ice to gas, jetting away from the surface and producing a small but measurable thrust. It's a natural process. It's been observed thousands of times. But 3i Atlas is no longer approaching the Sun. It's moving away. And outgassing typically diminishes with distance, not increases. By 10 UTC, someone in the meeting transcript uses the phrase solar sail. The room goes quiet. Solar sails are human technology. Thin sheets of reflective material, pushed by the pressure of sunlight, accelerating without fuel, without exhaust, riding the photon wind across the void. We've built them. We've tested them. The Japanese spacecraft Icaros proved the concept in 2010. NASA's NEA Scout was designed to use one before its mission failed in 2022, but we've never found one that we didn't build. The discussion shifts. The language becomes careful. The word artifact is used once, then retracted. The word anomalous is preferred. The data is tagged for further observation. The tracking schedule is extended. The web will continue to monitor 3i Atlas for as long as the geometry allows. 19 days, that's all they have. Meanwhile, the object continues to move. Its velocity is measured at 31.4 kilometers per second relative to the Sun. Slower than its initial detection speed of 47 kilometers per second, slowed by the Sun's gravity as it climbs out of the gravitational well. But the deceleration curve doesn't quite match the model. There's a residual, a persistent offset. Something is pushing it, or pulling it, or guiding it. The analysts weigh the options: solar outgassing, thermal recoil, radiation pressure, magnetic interaction with the solar wind. Each hypothesis is tested against the data. None fit perfectly, none are ruled out entirely. And then there's the albedo, cobalt blue. Dr. Rivas pulls up the spectral analysis from the initial detection months earlier. Back then, in the haste of discovery, the colour was noted but not emphasised. Interstellar objects are expected to be dark, reddened by eons of cosmic ray exposure, coated in carbon-rich organics that absorb most wavelengths of light. But 3 Atlas reflects, strongly, in a narrow band centered around 450 nanometers, blue, not the faint blue of scattered sunlight, but a vivid, almost metallic hue. The spectrum is run through mineral databases, no match. Organic ices are tested, no match. A synthetic comparison is attempted, materials used in spacecraft construction, anodized aluminum, treated polymers, experimental coatings developed for thermal control. Weak match. Probability, 12%. Not enough to conclude anything, just enough to keep the question alive. By the end of March 15th, the scientific community knows 3 things for certain. 1. 3 Atlas is not where it should be. 2. Its surface reflects light in a way that natural materials rarely do. 3. The window to study it is closing fast. The memos are sent. The observation schedules are revised. Ground-based telescopes are alerted. Radio observatories are asked to reserve time. The global network of instruments that watches the sky begins to turn its gaze toward a single point in space, a faint dot moving through the constellation of Pisces, 29 million kilometers away and receding. Somewhere in the data, hidden in the noise and the signal, in the photons and the electrons, the truth is waiting. But truth takes time, and time is the one resource no one has enough of. The stranger has been reacquired. Now, the real work begins. Chapter 2, March 20th, The Drift That Shouldn't Exist. 5 days later, the deviation has grown, not dramatically, not in a way that breaks the laws of physics or demands immediate explanation, but measurably, persistently, in a direction that continues to defy the clean mathematics of a purely gravitational trajectory. The object's velocity vector has shifted by 0.013 degrees since reacquisition. That's roughly 400 kilometers of displacement across its projected path. For a body travelling at over 30 kilometers per second, that's not a trivial error. That's not rounding. That's not the accumulated uncertainty of measurement. That's motion. Dr. Yuki Tanaka, an orbital dynamicist at the Japan Aerospace Exploration Agency, is the first to quantify it in terms that the broader community can grasp. He publishes a preprint on the Arxiv server, titled simply Non-Keplerian Trajectory of Interstellar Object 3I Atlas, Preliminary Analysis. The paper is 8 pages long. The conclusion is one sentence. The observed motion cannot be reconciled with gravitational forces alone. Within 12 hours, the paper has been downloaded 4,000 times. Within 24 hours, it's being discussed on every astronomy forum, every space news site, every podcast that covers the intersection of science and speculation. The term non-ballistic trajectory enters the public lexicon. And with it comes a question that no one in authority wants to answer directly. If gravity isn't the only force acting on 3I Atlas, what is? The most conservative explanation remains outgassing. Comets produce jets, ice sublimates, gas escapes. The process is asymmetric and asymmetry produces thrust. It's the rocket equation on a molecular scale, unintentional and uncontrolled, but real. But the data doesn't quite support it. Outgassing produces a detectable signature. A coma, a cloud of gas and dust surrounding the nucleus, a tail pushed away from the sun by solar wind and radiation pressure. Both have been searched for. Both are absent, or so faint that the most sensitive instruments can barely detect them. The Hubble Space Telescope is tasked with a deep stare. On March 18th, it spends 40 minutes locked onto the coordinates of 3I Atlas, using its wide-field camera 3 in the ultraviolet band, the wavelength where gas emissions shine brightest. The image is processed, enhanced, contrast stretched. There's something, a faint haze, but it's not the right shape. Instead of a symmetric coma spreading in all directions, there's a slight concentration along one axis, a directionality that suggests structure, not chaos. One researcher describes it as organized. Another calls it collimated. The language is careful, but the implication is clear. Whatever is happening on the surface of 3I Atlas is not random. On March 20th, the Keck Observatory in Hawaii adds its voice to the chorus. Using adaptive optics to compensate for atmospheric turbulence, Keck captures a series of high-resolution images in the near-infrared. The object is too small, too distant to resolve as anything more than a point of light. But the brightness fluctuates. A gentle oscillation, a pattern. The rotation period is calculated. 7.1 hours. That's slower than most comets, slower than most asteroids of comparable size. For a body shaped by collisions, by the chaos of formation and ejection from its home system, that's unusual, not impossible, just tidy. And then there's the drift. Dr. Tanaka's model is refined. Additional observations are folded in. Telescopes in Chile, in South Africa, in Australia contribute their data. The trajectory is recomputed with increasing precision. The result is the same. The object is accelerating, however slightly, in a direction that is not aligned with the sun's gravity, not aligned with the solar wind, not aligned with any known force that acts uniformly across the solar system. The term solar sail reappears in the briefings. This time it's not retracted. A solar sail would produce exactly this kind of signature, a continuous gentle acceleration in a direction determined by the orientation of the reflective surface. The pressure of sunlight is weak, just a few micronewtons per square meter, but over time, across millions of kilometers, it adds up. But solar sails are technology. They require construction, deployment, control. They don't form naturally in the cold of interstellar space. The debate fractures the community. One camp argues for patience, for more data, for the slow, methodical accumulation of evidence that either confirms a natural explanation or, by process of elimination, leaves room for the alternative. Another camp argues for urgency. The window is closing. In less than 2 weeks, 3 Atlas will pass beyond the optimal observation range for the Webb and Hubble. Ground telescopes will still track it, but with diminishing resolution. The moment to gather definitive data is now. A third camp, quieter and more cautious, begins to voice concerns about funding. The James Webb Space Telescope is the most expensive scientific instrument ever built. Its observing time is allocated in blocks measured in minutes, not hours. Every second pointed at 3i Atlas is a second not spent on distant galaxies, on exoplanet atmospheres, on the cosmic microwave background. The science return is weighted. The priorities are set by committees, and some on those committees are starting to ask whether an interstellar object with a trajectory anomaly justifies continued priority over other, more established research targets. The scientists push back. Dr. Rivas writes an open letter, co-signed by 43 astronomers from 12 countries. The letter is published on March 20th. It argues, in measured but firm language, that the study of interstellar objects is not a distraction from astrophysics. It is astrophysics. That every data point we gather about 3i Atlas is a data point about the processes that eject material from other star systems, about the composition of worlds beyond our Sun, about the diversity of objects that drift through the galaxy. And, the letter adds, if the trajectory anomaly is real, if it persists and strengthens, then we are witnessing something unprecedented, something that demands explanation, something that, in the history of astronomy, comes along perhaps once in a generation. The letter is careful not to use the word techno-signature, but the implication is there, woven between the lines, present in the choice of words and the emphasis on urgency. The response from the funding agencies is measured. NASA releases a statement affirming its commitment to the study of interstellar objects. ESA echoes the sentiment. Observing time is extended by another week. The Webb will continue to track 3i Atlas until the geometry makes it impossible. But no new resources are allocated. No emergency sessions are convened. The machinery of science moves slowly, bound by procedure and precedent. Meanwhile, the object continues to drift. The deviation grows, and somewhere, in the data streams and the observation logs, in the spectra and the images, the pattern becomes harder to ignore. This is not a comet behaving strangely. This is something else. Chapter 3. March 25th. The spectrum that echoed back. The radio pulse is detected at 2214 UTC on March 24th. The instrument is the Carl G. Jansky Very Large Array in New Mexico, a collection of 27 dish antennas, each 25 meters across, arranged in a Y-shaped configuration stretching across the high desert plain. The VLA is designed to listen, to capture faint whispers of radiation from distant galaxies, from pulsars and quasars, from the remnants of stars that died long before Earth formed. On this night, it is listening to 3i Atlas. The observation is part of a coordinated campaign. The VLA has been tasked with scanning the object across multiple frequencies, searching for any emission or reflection that might provide clues to its composition, its structure, its nature. Radio wavelengths can penetrate dust. They can reveal subsurface features. They can detect molecules that are invisible in optical light. The scan is routine. The expectation is minimal. Interstellar objects are typically radio quiet. They don't broadcast. They don't glow at centimeter wavelengths. But at a frequency of 1.42 gigahertz, corresponding to a wavelength of 21.1 centimeters, something comes back. Not noise, not static, a reflection. The VLA is not passively listening, it's transmitting. A brief, low-power pulse, aimed at the coordinates of 3i Atlas, followed by a listening phase. The technique is called radar astronomy. It's been used for decades to study asteroids, to measure their distance and velocity, to map their surfaces with a precision that optical telescopes cannot achieve. But interstellar objects are too far, too faint for radar, to work. The inverse square law is merciless. The power required to bounce a detectable signal off an object at tens of millions of kilometers exceeds what most facilities can produce. And yet, the signal returns, delayed by 11.2 seconds. That's the light travel time, the round trip. The signal leaves the VLA, crosses 29 million kilometers, reflects off something, crosses back, and arrives at the receiver's 11.2 seconds later. The strength is faint, just above the noise floor, but it's there, repeatable, consistent across 3 separate pulses. Dr. Aaron Mburu, the radio astronomer leading the observation, stares at the data for 10 minutes before calling his supervisor. He's seen echoes before, from the moon, from near-Earth asteroids, from spacecraft. but never from an interstellar object. The geometry is checked, the timing is verified, the frequency is locked, the signal is real, and then the analysis deepens. The echo is not a simple reflection, it's modulated. The returned pulse has structure, a slight variation in amplitude, a harmonic that wasn't present in the original transmission. It's subtle. It could be an artifact of the object's rotation, the way the surface geometry changes the reflection pattern as the body tumbles through space. But it could also be something else. By March 25th, the data has been shared with the broader radio astronomy community. Teams at the Arecibo Observatory in Puerto Rico, still operational in this timeline, its massive dish repaired and upgraded after damage in 2020, request confirmation. Teams at the Meerkat Array in South Africa prepare their own observations. The debate begins immediately. One camp argues that the echo is a resonance artifact, that the surface of 3I Atlas contains structures, cracks, ridges, cavities, that happen to resonate at the specific frequency transmitted by the VLA. It's a coincidence, a product of geology and geometry, not design. Another camp points out that resonance requires symmetry, that natural surfaces shaped by impacts and weathering do not typically produce coherent echoes, that the probability of a random object reflecting a signal at precisely the wavelength most commonly used for hydrogen mapping, and historically for theoretical interstellar communication, is low. Not zero, but low. The probability is calculated by Dr. Embaru's team. They fold in the geometry, the rotation period, the albedo, the frequency match. They run Monte Carlo simulations, testing thousands of random surface configurations to see how many produce a similar echo pattern. The result? 1 in 47. That's not statistically significant. Not yet. In astronomy, the threshold for claiming a discovery is typically 1 in 3.5 million, the 5 sigma standard. The echo's interesting, it's unusual, but it's not proof of anything. Still, the term engineered reflectivity appears in one of the internal reports. It's not published. It's not shared beyond a small circle of researchers who have access to the raw data. But it's there, in the record, in the conversation. Because engineered surfaces do this. Radar reflectors, corner cubes, phased arrays. These are technologies designed to bounce signals back with precision, to appear bright to radar even when they're small, to create an echo that stands out against the cosmic background. We use them on Earth, on satellites, on spacecraft, on the retroreflectors placed on the Moon by Apollo astronauts, still bouncing laser pulses back after more than 50 years. But we've never found one that we didn't put there. The observation window continues. The VLA sends additional pulses. The echo returns, fainter now as the object recedes, but still detectable. The structure persists. The modulation is consistent. On March 25th, at 14:00 UTC, a second facility confirms the result. The Meerkat Array in South Africa, using 64 dishes spread across 8 kilometers of the Karoo Desert, detects the same echo. The timing matches. The frequency matches. The amplitude is slightly different, a function of geometry and orientation, but the signature is the same. 2 independent observations, same result. The threshold for dismissing it as noise or error rises, but the threshold for claiming it as evidence of anything extraordinary remains distant. The scientific method is slow. It is built on replication, on skepticism, on the careful accumulation of data that survives scrutiny. It does not leap to conclusions. It does not favor drama over detail. And yet, beneath the calm language of the reports, beneath the careful phrasing and the probabilistic caveats, there is a current of unease. Because the echo's not behaving like geology. It's behaving like something that knows it's being watched. Chapter 4, March 29th. Starship's silent pivot. The rumour begins on a forum, not an official source, not a press release or a peer-reviewed paper or a statement from a government agency. A forum, a place where space enthusiasts gather to pass launch schedules, to analyse regulatory filings, to track the movements of ships and payloads and personnel in the endless effort to predict what comes next. The post is made at 03:42 UTC on March 28th by a user with a history of accurate leaks, a track record that has earned cautious credibility. The post reads, Starship XL manifest updated, Block 3 variant, extended deep space test. Launch window April 10th to 15. Payload TBD. Whispers of a 3i window. Within an hour, the post has been screenshotted, shared across social media, dissected by analysts who track the aerospace industry with the precision of intelligence operatives. SpaceX does not comment. They rarely do. The company's communication strategy has always favoured demonstration over declaration, preferring to let the hardware speak for itself. But the evidence begins to accumulate. On March 29th, a filing appears in the Federal Communications Commission database, a request for experimental radio licenses covering frequencies typically used for deep space communication. The applicant is listed as a subsidiary of SpaceX. The operational zone is listed as cislunar and beyond. Cislunar means the space between Earth and the Moon. Beyond means further. Later that day, maritime tracking data shows a SpaceX recovery vessel departing Port Canaveral, heading not toward the usual downrange zones used for booster recovery, but toward a position in the Atlantic that corresponds to a much higher energy trajectory. And then there's the payload. Starship XL is the latest evolution of the fully reusable launch system that has redefined access to space over the past 3 years. Taller than the Saturn V, more powerful than any rocket in history, capable of lifting over 150 tons to low Earth orbit or 40 tons to escape velocity, the speed needed to leave Earth's gravitational influence entirely. The Block 3 variant is new. It features extended propellant tanks, improved Raptor engines, upgraded heat shielding for high-speed re-entry. It's designed for missions that go beyond the Moon, to Mars, to the asteroid belt, to intercept trajectories. The term 3-eye window is cryptic. It doesn't appear in any official documentation, but those who follow the mission closely understand the implication. A window in spaceflight terminology refers to a period when the geometry of orbits aligns, when a launch can be timed to reach a specific target with minimal fuel expenditure. If Starship XL is planning a 3-eye window, that means one thing. The trajectory is being designed to pass near the coordinates of 3-eye Atlas, not rendezvous. The object is moving too fast, too far for a crewed or even robotic mission to match velocity and dock. But a flyby, a close approach, near enough to deploy instruments, to observe, to gather data that cannot be obtained from Earth or from telescopes in orbit around Earth. The speculation intensifies. By the afternoon of March 29th, aerospace journalists are pressing SpaceX for confirmation. The company's standard response is deployed. We do not comment on rumoured missions or speculative manifests. But the silence is not denial. And then, late in the day, a secondary source emerges. An internal memo leaked to a reporter at Aviation Week and Space Technology describes a payload integration at SpaceX's Starbase facility in Texas. The payload is described as a sensor array. Mass, approximately 2 tons. Dimensions, compact enough to fit within Starship's payload bay. Purpose, unspecified. But the memo includes a notation: deployment profile, ballistic coast, passive observation, high-gain telemetry. Ballistic coast means no propulsion after separation from the main vehicle. Passive observation means sensors, not active probes. High-gain telemetry means a long-distance data link, designed to transmit large volumes of information back to Earth from far beyond the Moon. The pieces fit. By evening, the story has been picked up by major outlets. The New York Times runs a headline: SpaceX may be preparing mission to study interstellar object. The article is careful. It cites anonymous sources. It emphasizes that nothing has been confirmed. But it quotes Dr. Emily Zhao, a planetary scientist at Caltech. If this is real, it represents a significant shift in how we approach interstellar object studies. Government missions take years to plan. Private missions can move faster. If SpaceX can get a sensor package near 3-eye Atlas before it leaves observable range, the data would be invaluable. The article also notes the political dimension. NASA has been studying interstellar objects for decades. The scientific community has proposed missions, written white papers, lobbied for funding. But the budgets have never materialized. The timelines stretch too long. The windows close before the missions launch. A private mission bypasses all of that. It operates on a different timeline, with different incentives. It doesn't need congressional approval. It doesn't need peer review. It needs a rocket, a payload, and a launch window, and SpaceX has all three. The reaction within the scientific community is mixed. Some see it as an opportunity, a chance to gather data that would otherwise be lost, a demonstration that the private sector can complement even accelerate the pace of discovery. Others see it as a risk, a lack of transparency, a mission conducted without the oversight, without the peer review, without the public accountability that defines publicly funded science. Dr. Ravers, speaking at a conference in Vienna on March 30th, offers a measured take. If SpaceX is indeed planning a mission, we hope they will share the data openly. Science thrives on transparency. The questions raised by 3i Atlas are too important to be answered behind closed doors. But she also acknowledges the reality. The window is closing. If a private mission can gather data that we would otherwise never obtain, then we have to consider whether the perfect is the enemy of the good. As March draws to a close, the pieces remain scattered. Rumours, leaks, unconfirmed reports. No official statement from SpaceX, no launch schedule posted on their website. But the recovery vessel is at sea, the payload is integrated. And somewhere in the trajectory planning offices, in the mission control rooms, in the quiet conversations between engineers and scientists, a plan is taking shape, a plan to reach out, to cross the gap, to see what's really out there before the chance is gone. Chapter 5, April the 2nd, the element that shouldn't form. The spectral line is labelled 217. It appears in the data from the Atacama Large Millimeter Submillimeter Array, ALMA, a collection of 66 radio dishes perched at 5,000 meters elevation in the Chilean Andes, where the air is thin and the sky is among the clearest on Earth. ALMA observes at wavelengths between infrared and radio, a regime where molecules glow, where the fingerprints of chemistry are written in the rotation and vibration of atoms bound together, spinning in the cold of space, radiating energy in precise quantized steps. The observation of 3i Atlas is scheduled for April 1st, a 12-hour integration designed to capture the faint emissions from any volatiles outgassing from the surface: water, carbon monoxide, methane, the usual suspects in cometary composition. The data is processed on April 2nd, and there, in the spectrum at a frequency of 214.3 GHz, is a spike. Narrow, distinct, strong enough to be unambiguous. Dr. Sofia Mendez, the radio astronomer reviewing the data, runs the identification protocol. The frequency is compared against databases of known molecular transitions. Thousands of molecules have been catalogued. Their spectra are mapped. Their signatures are distinct. The match comes back: technetium-99. Dr. Mendez stares at the result. She runs the identification again. Same result. She calls her colleague, Dr. Ravi Sengupta, who is working at the same facility but on a different project. He arrives 10 minutes later, reviews the data, runs his own independent analysis. He sees the same line: technetium-99. The problem is simple. Technetium doesn't form naturally in stable environments. It's a synthetic element. Element 43 on the periodic table. The lightest element that has no stable isotopes. Every form of technetium is radioactive, decaying over time into other elements. Technetium-99 specifically has a half-life of 211,000 years. That sounds long. But on cosmic timescales, the millions and billions of years that asteroids and comets have existed, it's a blink. Any technetium that formed when the solar system was born has long since decayed into ruthenium. Technetium can be created in supernovae, in the collisions of neutron stars, in the cores of certain types of stars. But those environments are violent. The technetium is ejected into space, where it dilutes, spreads, decays. Finding it in an interstellar object, in concentration strong enough to produce a detectable spectral line, is unexpected. Not impossible, but unexpected. Dr. Mendez tags the data as anomalous and submits it for review. The standard procedure, the cautious approach. The line will be examined by other researchers, checked for instrumental artifacts, tested against models of cometary composition. But before that review can complete, a second confirmation arrives. The submillimeter array in Hawaii, observing 3 Atlas on a different night, at a different frequency, detects the same signature. The line is slightly shifted, a Doppler effect from the object's motion, but the identification is unmistakable. Technetium, SNINCH, 2 independent observatories, same result. The data is no longer anomalous, it's verified, and the questions begin: how does an interstellar object carry detectable amounts of a radioactive element that should have decayed long ago? The first hypothesis is recent formation. if 3I Atlas was ejected from its home star system relatively recently, within the last few 100,000 years, then the technetium could still be present. Some stars produce technetium in their outer layers if the object formed from material shed by such a star, and if it was ejected soon after, the signature could persist. But 3 Atlas is moving at 47 kilometers per second relative to the Sun. That's fast. Too fast to have originated from a nearby star. Tracing the trajectory back, accounting for the gravity of the Milky Way, the most likely origin is hundreds of light years away. At that distance, even travelling at high speed, the journey would take millions of years, far longer than technetium-99's half-life. The second hypothesis is contamination. Perhaps the object passed through a region of space enriched in technetium, the remnant of a supernova, a stellar wind, a neutron star merger. Perhaps the surface absorbed trace amounts, and that's what's being detected. But the spectral line is strong, stronger than trace contamination would produce, and the absorption would need to be recent. Within the last few 100,000 years, the coincidence strains credibility. The third hypothesis is not spoken aloud in the formal reports, but it appears in private messages, in late-night emails, in the conversations that happen after the official meetings end. Technetium is used in nuclear medicine, in radioisotope thermoelectric generators, RTGs, the power sources that drive spacecraft like Voyager, like Curiosity, like New Horizons. It's a byproduct of nuclear reactors, of controlled fission. If you were building something, a probe, a vessel, a structure designed to travel between stars powered by radioactive decay, emitting heat over centuries, you might use technetium, or something like it. The hypothesis is not published. It's too speculative, too far from the conservative core of planetary science, but it's there, in the record, in the minds of those who see the data and cannot explain it away. On April 2nd at 18:00 UTC, Dr. Mendez submits a second report. This one includes a recommendation. Continued high-resolution spectroscopy recommended. Target additional radioactive isotopes. Cross-reference with models of artificial power sources. The phrase, artificial power sources, is as close as the report comes to saying what some are thinking, but it's enough. By April 3rd, the discovery is being discussed in closed-door meetings at NASA, ESA and JAXA. The data is shared with nuclear physicists, with engineers who design space probes, with analysts who assess technosignatures. The response is measured, cautious, but not dismissive, because the chemistry doesn't fit the natural models, and the window is still open. For now. Chapter 6. April 5th. The Reflective Code. The discovery is made by someone who isn't an astronomer. His name is Mateo Ruiz. He's a software engineer in Santiago, Chile, working for a tech company that develops machine learning algorithms for pattern recognition. He's 32 years old. He has no formal training in astrophysics, but he has access to the public data archives where observatories post their raw observations, and he has the tools to analyze them. He's been following the 3I Atlas story with the casual interest of someone who loves space, but doesn't work in the field. When the ALMA data is released on April 4th, standard practice for publicly funded observations after a brief proprietary period, he downloads it out of curiosity. He's not looking for anything in particular. He just wants to see the spectrum, to visualize the data, to play with the signal processing techniques he uses in his day job. He loads the data into his software. He applies a Fourier transform to convert the time series signal into frequency space. He enhances the contrast. He filters out the noise, and he sees something, a pattern. Not in the spectral lines themselves, but in the spacing between them. The peaks in the spectrum, the frequencies where molecules emit light, are not random, they're clustered, and the clustering has structure. He isolates the peak positions, he calculates the intervals between them, and he finds a sequence: 1, 2, 3, 5, 8, 13, 21. The Fibonacci sequence. He stares at his screen for a long time, then he runs the analysis again, assuming he made an error. Perhaps he's seeing a pattern where none exists. Pareidolia. The human tendency to find meaning in randomness. The sequence remains. He expands the dataset. He pulls in the VLA observations, the Meerkat data, the earlier spectra from the James Webb. He applies the same analysis. He looks for the pattern across different wavelengths, different instruments, different dates. It's there, faint. Incomplete in some datasets, but consistent where the signal-to-noise ratio is high enough to resolve individual peaks. He writes a script to quantify the probability. He generates synthetic spectra, random distributions of peaks, and tests how often the Fibonacci pattern appears by chance. The result? 1 in 22,000. That's far beyond coincidence. That's structure, intentionality, or a very, very strange natural process that no one has ever observed before. On April 5th at 9:15 UTC, Matteo posts his findings on an open-access preprint server. The paper is titled Mathematical Symmetry in the Spectral Emission of Interstellar Object 3I Atlas. The paper is 7 pages. It includes the raw data, the analysis code, the probability calculations. It's methodical, it's transparent, it invites replication. Within 6 hours, the paper has been downloaded 12,000 times. Within 12 hours, it's being discussed on every major science platform. Within 18 hours, it's being replicated by 3 independent teams, all of whom confirm the core finding. The spectral peaks are not randomly spaced, and within 24 hours, the data vanishes from the public archive. The removal is noticed immediately. The ALMA data portal, which had hosted the full spectral dataset, now shows an error message. Data temporarily unavailable for calibration review. The excuse is plausible. Data is sometimes pulled for recalibration, for quality checks, for error correction. It happens. But the timing is suspicious. Matteo's paper is still live. The preprint server doesn't remove it, but several of the datasets he linked to, the supporting files, the raw observations, are no longer accessible. The forums erupt. Conspiracy theories proliferate. Claims of a cover-up, accusations of suppression. The language is heated, the speculation wild. But beneath the noise, there are calm voices. Scientists who note that data embargoes are not unprecedented, that sensitive findings are sometimes withheld until they can be thoroughly vetted, that the scientific process demands caution, especially when the implications are extraordinary. Dr. Rivas, asked to comment by a journalist, offers a measured response. Mathematical patterns in spectral data can arise from resonance effects, from instrumental harmonics, from interference between signals. These need to be ruled out before we conclude that the pattern is intrinsic to the object. The removal of data for recalibration is standard practice. We should wait for the official review. But privately, in an email to a colleague, she writes, "I don't like it. If the pattern is real, hiding it doesn't make it go away. It just makes us look like we're afraid of the answer." The debate intensifies over the next 48 hours. Some argue that the pattern is an artifact, that Matteo's analysis, while clever, has overfit the data, that the Fibonacci sequence is easy to find if you look hard enough, especially in noisy data where you can adjust the peak position slightly to match the pattern. Others argue that the replication by independent teams undermines that critique, that 3 different groups using different methods found the same result, that the probability is too low to dismiss. And then there's the question of mechanism. If the pattern is real, if the spectral peaks are genuinely spaced according to a mathematical sequence, what could cause it? Natural processes can produce periodic structures. Crystals, for example, have lattice spacings that follow mathematical relationships. Molecules have vibrational modes that are quantized, that follow harmonic series. But the Fibonacci sequence doesn't appear in molecular spectra. It doesn't arise from the quantum mechanics of atomic transitions. It appears in biology, in the arrangement of leaves on a stem, in the spiral of a nautilus shell, in the branching of trees. It appears in art, in architecture, in music. It appears in systems that grow, that organize, that optimize. It appears in systems that are designed. The word is not used in the official discussions, but it's there, in the subtext, in the choice of phrasing, in the way the conversation shifts whenever someone mentions the pattern. On April 7th, the ALMA data is restored to the public archive. A brief statement is issued. Recalibration complete. No significant errors found. Data reposted. The spectrum is unchanged. The peaks are in the same positions. The pattern remains. Matteo's paper gains a new section, updated after peer feedback. While the mathematical structure observed in the spectral data is statistically significant, the physical mechanism remains unexplained. Further observations and theoretical modelling are required. It's a careful conclusion, a scientist's conclusion, but it leaves the door open because the pattern is real, and no one knows why. Chapter 7, April 10th. The Alignment Day. The geometry is perfect. On April 10th, at 14:23 UTC, the orbital planes align. Earth's path around the Sun and the trajectory of 3 Atlas intersect. Not physically, but mathematically. The object crosses the plane of the ecliptic, the flat disk in which most of the planets orbit, moving from south to north at an angle of 31 degrees. For a brief window, 6 hours, the line of sight from Earth to 3I Atlas is unobstructed by the Sun's glare, unmarred by atmospheric distortion, optimal for observation. The telescopes are ready. The Hubble Space Telescope, orbiting 400 kilometers above Earth, has been repositioned. Its fine guidance sensors are locked onto the coordinates. Its advanced camera for surveys is active, configured for maximum resolution in the visible spectrum. The James Webb Space Telescope, far beyond the Moon at the L2 Lagrange point, mirrors the observation in the infrared. Its 18 hexagonal mirrors, coated in gold, gather photons that have travelled 28 million kilometers from the surface of the object. On the ground, the Keck Observatory in Hawaii, the Very Large Telescope in Chile, and the Gran Telescopio Canarias in Spain coordinate their observations. Each facility targets 3 Atlas during its transit across the sky, each capturing data at different wavelengths, different times, different angles. The goal is simple: to resolve the object, to see its shape, its structure, its surface features, to move beyond spectroscopy and radar and mathematical patterns, and to simply look. The data begins to arrive at 15 km UTC. The first image from Hubble is processed within 30 minutes. The object is faint, magnitude 23.6 near the limit of what Hubble can detect. But it's there, a smudge against the background of distant stars. The image is enhanced, contrast stretched, deconvolved to remove the blurring effects of the telescope's optics, and a shape emerges, not a sphere, not an ellipsoid, not the irregular, potato-like form of a typical asteroid. Angular. The outline is jagged, composed of straight edges and sharp vertices. It's not uniform. One side is brighter than the other, reflecting more light, suggesting a difference in composition or texture. Dr. Mbaru, reviewing the image at the Goddard Space Flight Center, describes it in his notes: geometry inconsistent with collisional evolution, faceted, possibly crystalline. The rotation is tracked across the 6-hour window. The object tumbles slowly, 7.1-hour period, and as it rotates, different faces come into view. Each face reflects light differently. Some are dark, absorbing almost all the sunlight that strikes them. Others are brilliant, flashing like mirrors. The variation in brightness is extreme. A factor of 12 between the dimmest and brightest phases. That's unusual. Most asteroids vary by a factor of 2 or 3. The smooth distribution of surface materials, the gradual weathering by micrometeorite impacts, tends to homogenize the reflectivity. But 3I Atlas has surfaces that behave as if they've been polished, or coated, or structured. The James Webb data adds depth. In the infrared, the object glows faintly with thermal emission, the heat absorbed from the sun and re-radiated into space. But the glow is not uniform. There are hot spots and cold spots, patches that differ in temperature by as much as 50 Kelvin. That's a huge variation for a body in thermal equilibrium. Dr. Tanaka, analysing the thermal map, offers a tentative explanation. Variable thermal inertia. Different materials conduct heat at different rates. If the surface is a patchwork of ice, rock, and something else, metal, that could explain the temperature gradients. But the something else remains undefined. The ground-based telescopes contribute their own data. The Gran Telescopio Canarias, using adaptive optics to compensate for atmospheric turbulence, captures a series of high-resolution images in the near-infrared. The resolution is lower than Hubble's, but the wavelength coverage is broader. And in those images, there are shadows, faint, barely perceptible, but present. Shadows require topography. They require structures that rise above the surface, that block the light of the sun, that cast darkness onto adjacent regions. The images are processed, the shadows are analysed, and a preliminary height map is constructed. The result shows protrusions, ridges, features that extend several hundred meters above the surrounding terrain. Dr. Zhao, the planetary scientist at Caltech, reviews the data with her team. She's been vocal throughout the observation campaign, advocating for transparency, for caution, for the rigorous application of the scientific method. But when she sees the shadows, she pauses. In a video conference later that evening, she speaks carefully. Ice fracturing can create ridges. Thermal stress can cause surface materials to buckle, to form raised features. But the distribution here is organized. The ridges are parallel. They're evenly spaced. A colleague asks the question everyone is thinking. Could it be a lattice? Dr. Zhao hesitates. Then, I don't know. The term lattice is loaded. It implies regularity, structure, order. Lattices exist in nature, in crystals, in the hexagonal columns of basalt that form when lava cools slowly, in the polygonal patterns of desiccation cracks in dried mud. But those are small-scale features, centimetres, metres, not the hundreds of metres suggested by the shadows on 3i Atlas, and lattices in engineering are something else. They're frameworks, scaffolds, structures built to be strong and light to distribute stress to support loads. The debate that follows is intense but quiet. It doesn't happen in public forums or press releases. It happens in private meetings, in encrypted email threads, in phone calls between researchers who trust each other enough to speak freely. Some argue that the mind sees patterns where none exist, that the shadows could be artifacts of the imaging process, of the way light scatters off an irregular surface, of the assumptions built into the processing algorithms. Others argue that the regularity is too pronounced to ignore, that multiple instruments, multiple wavelengths, multiple observation geometries all show the same features. One researcher, speaking anonymously to a journalist, summarizes the tension. We're trained to look for natural explanations first, and we should. But at some point, if every natural explanation requires increasingly unlikely coincidences, we have to consider the alternative. The alternative is not named, but everyone knows what it is. By the end of April 10th, the alignment is over. The object has moved on, continuing its trajectory outward from the Sun. The window has closed, the data remains. And in the images, in the shadows, in the facets, and the ridges, and the angular geometry, the question persists. What are we looking at? Chapter 8. April 15th. The disagreement at L2. The meeting is not public. It takes place in a secure video conference, participants scattered across 3 continents, connected by encrypted channels, bound by non-disclosure agreements that prevent them from sharing what's discussed until the review process is complete. The participants represent the steering committee for the James Webb Space Telescope, directors from NASA, senior scientists from ESA, representatives from the Canadian Space Agency, and the Space Telescope Science Institute, 16 people in total. The agenda has one item: continuation of 3i Atlas observing campaign. The discussion begins at 13 UTC on April 15th. Dr. Rivas presents the case for continuation. She summarizes the findings to date: the trajectory anomaly, the radar echo, the spectral pattern, the technetium signature, the angular geometry observed during the alignment. She speaks for 12 minutes. Her tone is measured. She emphasizes uncertainty. She avoids speculation. But she concludes with a clear recommendation. The object exhibits multiple anomalies that cannot be explained by current models of natural interstellar bodies. Continued observation is scientifically justified. The response is divided. Dr. Marcus Leone, a senior program scientist at NASA headquarters, speaks next. He acknowledges the findings but raises concerns about resource allocation. The Webb is oversubscribed. For every hour spent observing 3i Atlas, another approved program is delayed. High redshift galaxies, exoplanet atmospheres, solar system targets. He doesn't question the science. He questions the priority. We have a responsibility, he says, to balance immediate opportunities against long-term objectives. 3i Atlas is intriguing, but we need to ask, what is the expected science return, and how does that compare to other uses of the telescope? Dr. Rivas responds, the expected return is potentially transformative. If even one of the anomalies proves to be non-natural in origin, the implications extend far beyond planetary science. Dr. Leone counters, and if they all have natural explanations that we simply haven't identified yet, we could spend weeks on this object and conclude that it's a comet with unusual but explicable properties. The debate continues. Others join in. Dr. Amara Okafor, an astrophysicist from the Space Telescope Science Institute, supports continued observation, but proposes a compromise. Reduce the observing time. Focus on the most critical measurements. We don't need continuous monitoring. We need targeted snapshots that can test specific hypotheses. Dr. Sengupta, the radio astronomer who confirmed the technetium signature, pushes back. The object is receding. Every day the signal weakens. If we reduce the cadence, we may miss transient phenomena. Emissions, outbursts, changes in the radar echo. Continuous observation is the only way to capture a complete picture. A representative from ESA, Dr. Klaus Reinhardt, raises a different concern. There's also the matter of public perception, the data leaks, the speculation, the removal and restoration of the ALMA dataset. We're operating in an environment where every decision is scrutinized, where the absence of transparency fuels conspiracy theories. If we continue to prioritize 3i Atlas without clear justification, we risk politicizing the science. Dr. Rivas responds sharply. The science is the justification. We don't adjust our observation strategy based on public relations concerns. Dr. Reinhardt concedes the point, but presses the issue. I'm not suggesting we do. I'm suggesting we communicate more effectively. If we're going to continue observing this object, we need to explain why, clearly, publicly, before the narrative is defined for us. The conversation shifts to the question of classification. Dr. Leone suggests that new data, particularly the findings related to the spectral pattern and the angular geometry, should be reviewed internally before public release. Not to suppress anything, he clarifies, but to ensure that we're not disseminating preliminary results that could be misinterpreted. Dr. Okafor disagrees. Delaying release creates exactly the perception that Dr. Reinhardt is concerned about. It suggests we have something to hide. The standard practice is to release data after a brief proprietary period. We should stick to that. Dr. Leone. Standard practice assumes standard findings. These are not standard. Dr. Okafor. Which is exactly why they should be shared. Extraordinary claims require extraordinary scrutiny. That scrutiny comes from the broader community, not from a closed committee. The debate intensifies. Voices overlap. The moderator intervenes, calling for a vote. The question is put forward. Should observing time for 3i Atlas be extended beyond the currently allocated window? The vote is taken. 8 in favour, 7 opposed, 1 abstention. The margin is narrow, but the result is clear. Observing time is extended, but with conditions. The cadence is reduced. The focus shifts to high-priority measurements, spectroscopy at multiple wavelengths, radar follow-up, thermal mapping. The data will be reviewed by an internal panel before public release. The meeting adjourns at 15:47 UTC. No public statement is issued. But within hours, word of the vote leaks. A participant, frustrated by the restrictions on data release, shares the outcome with a trusted journalist. The headline appears the next morning. NASA extends 3 Atlas observations amid internal debate over data transparency. The article is accurate but incomplete. It captures the tension, the division, the cautious compromise, but it doesn't convey the depth of the disagreement, the weight of the decision, the sense among some of the participants that they are navigating unprecedented territory. Because the anomalies are not resolving, they're accumulating, and somewhere in the data, in the signals and the spectra, in the shadows and the echoes, the object is still speaking, still reflecting, still waiting to be understood. Meanwhile, something else is happening. At 21:14 UTC on April 15th, the VLA detects a new signal, not a reflection this time, an emission, faint, narrow band, centered at the hydrogen line, 21.3 centimeters. The signal pulses, once every 3 hours, 12 minutes. The statistical probability that this is random noise, 1 in 20,000. The memo is drafted, the findings are logged, the data is flagged for immediate review. And in the meeting rooms, in the observatories, in the minds of those who have been watching 3i Atlas since it reappeared from behind the sun, the unspoken question grows louder. What if we're not just observing? What if something is observing us? Chapter 9, April 19th. The light that didn't scatter. The observation is planned as a routine photometric study. The European Southern Observatory's Very Large Telescope in Chile targets 3i Atlas on the night of April 18th. Four 8.2-meter mirrors work in unison. Their light combined through interferometry to achieve resolution equivalent to a single telescope 130 meters across. The goal to measure how sunlight scatters off the object's surface across a range of wavelengths. This technique, called spectrophotometry, reveals the composition and texture of distant bodies. Rough surfaces scatter light diffusely. Smooth surfaces reflect it specularly, like mirrors. Different minerals absorb and reflect different colors. The data is expected to confirm what earlier observations suggested. A mixed surface, patches of ice and rock, some regions rough and some regions smooth. But when the data is processed on April 19th, something else appears. The sunlight reflecting off 3i Atlas is not scattering. Dr. Yuki Tanaka, reviewing the photometric curves at JAXA's Institute of Space and Astronautical Science in Tokyo, notices it first. The spectrum is too clean, too coherent. When sunlight hits a natural surface, rock, ice, regolith, it scatters in all directions. The reflected light becomes diffuse, its spectrum broadened and blurred by the randomness of the surface structure. But the light from 3i Atlas retains its spectral purity. The wavelengths that arrive from the Sun are reflected without significant dispersion. The peaks in the solar spectrum, the Fraunhofer lines where specific elements in the Sun's atmosphere absorb light, are still visible in the reflected light, sharp and well-defined. It's as if the surface is behaving like a filter, or a lens, or something that controls the way light interacts with it. Dr. Tanaka runs the analysis 3 times. He checks the calibration. He compares the results to observations of other asteroids made with the same instrument on the same night. The other asteroids scatter normally. Their spectra are diffuse, broadened, messy. 3i Atlas does not. He writes an email to Dr. Rivas, copying Dr. Zhao and Dr. Sengupta. Anomalous photometric behavior detected. Reflected sunlight shows minimal spectral dispersion. Possible explanations: 1. Surface coated with highly smooth material. 2. Adaptive or layered surface structure. 3. Instrumental artifact. Request independent confirmation. The request is answered within 24 hours. The Keck Observatory repeats the observation on April 19th, using a different instrument, a different telescope, a different atmospheric path. The result is the same. The reflected light is clean. The spectrum is coherent. The term adaptive surface is now in writing. Adaptive surfaces are not unknown. They exist in nature. The scales of certain fish change their reflectivity based on the angle of light. The wings of some butterflies have microstructures that produce iridescent colors by interference, not pigment. But those are biological, evolved, optimized over millions of years to serve specific purposes: camouflage, communication, thermoregulation. Could a geological process produce something similar? Dr. Zhao convenes a teleconference on April 20th. 15 researchers join. The discussion is technical, dense with jargon, and references to papers on surface physics and material science. One hypothesis is that the surface is coated with a thin layer of ice that has been annealed, heated and cooled slowly to form a smooth, crystalline structure. This could reduce scattering, but the thermal data doesn't support it. The surface temperatures vary too much. Annealed ice would sublime, crack, roughen under the thermal stress. Another hypothesis is that the surface is covered in glassy material. Impact melt from ancient collisions, flash heated and then rapidly cooled into an amorphous solid. Glass can reflect light coherently, but the angular geometry, the facets and ridges observed during the alignment, doesn't match the smooth, flowing forms that impact melt typically produces. A third hypothesis, offered tentatively by a material scientist from MIT, is that the surface could be a metamaterial, a synthetic structure designed to control the propagation of light. Metamaterials can exhibit properties not found in nature: negative refractive indices, perfect lenses, cloaking devices. They're also, as far as anyone knows, exclusively human inventions. The suggestion is met with silence. Then Dr. Zhao speaks. Let's set aside the question of origin for the moment. What we're observing is a surface that reflects light without significant scattering. Can we test that hypothesis directly? Dr. Tanaka proposes a polarimetry study. Polarization, the orientation of light waves, changes predictably when light scatters off rough surfaces versus smooth surfaces. By measuring the polarization of the reflected light from 3i Atlas, They can quantify the degree of surface smoothness. The observation is scheduled for April 21st. Meanwhile, the signal continues. The pulse at 21.3 centimeters, detected by the VLA, repeats with clockwork regularity, 3 hours, 12 minutes. The period is constant to within milliseconds. The strength varies slightly, modulated by the object's rotation, but the timing does not waver. The Meerkat Array in South Africa confirms the signal. The Arecibo Observatory in Puerto Rico detects it. 3 independent facilities, 3 continents, same result. The signal is real, the signal is persistent, and the signal is coming from the same object that reflects light without scattering, that carries technetium, that moves on a trajectory that defies pure gravitational prediction. On April 20th at 19:30 UTC, an unscheduled press briefing is announced by NASA. The timing is unusual. The announcement gives less than 12 hours notice. The briefing takes place at 10 CE UTC on April 21st. Dr. Leone speaks for NASA. Dr. Reinhardt represents ESA. Dr. Rivas is present but does not deliver remarks. Dr. Leone's statement is brief. Recent observations of interstellar object 3I Atlas have revealed several properties that are not yet fully understood. These include trajectory deviations, spectral anomalies, and surface characteristics that differ from typical cometary or asteroidal bodies. NASA, in coordination with international partners, is continuing to study the object. All data will be made publicly available following standard review procedures. We encourage the scientific community to engage with this data and contribute to the analysis. A reporter asks, "Are you saying the object is artificial?" Dr. Leone responds, "We are saying the object is unusual. We are not drawing conclusions until the data has been thoroughly analysed." Another reporter, "Is there a signal?" Dr. Reinhardt, "There are radio emissions that are under investigation. Their origin has not been conclusively determined. The briefing lasts 17 minutes. No images are shown, no spectra are displayed. The language is careful, neutral, designed to inform without alarming, to acknowledge without speculating. But the tone is different. There's a weight to the words, an undercurrent of something unspoken. The headlines that follow are predictable. NASA confirms anomalies in interstellar object. Mysterious radio signals detected from 3I Atlas. Scientists baffled by unusual visitor from beyond solar system. The speculation explodes. The forums overflow. The conspiracy theories multiply. But beneath the noise, the data continues to arrive, and the light that didn't scatter remains unexplained. Chapter 10, April 23rd, Signal 21.3. The confirmation comes at 02:34 UTC on April 23rd. The signal, tracked continuously for 8 days by the combined arrays of the Very Large Array in New Mexico, the Meerkat facility in South Africa, and the refurbished Arecibo Observatory in Puerto Rico, is isolated to a source region within 400 kilometers of 3 Atlas's calculated barycenter. 400 kilometers, at a distance of 27 million kilometers. That's extraordinary precision. It's like identifying the source of a sound in a stadium from the other side of a city. The technique is called interferometry. By combining the signals from multiple telescopes separated by thousands of kilometers, astronomers create a virtual dish as large as the Earth itself. The resolution is sufficient to pinpoint not just the object, but a specific region on or near its surface. The signal is narrowband. It occupies a frequency range of less than 1 kHz, centered at 1.42 GHz, the hydrogen line, the most abundant element in the universe, the wavelength chosen decades ago as the universal channel for hypothetical interstellar communication. But it's not just the frequency that's remarkable, it's the structure. Dr. Mburu, the radio astronomer who first detected the radar echo, leads the analysis. He extracts the signal from the noise using a technique called matched filtering, comparing the observed data against a template of expected patterns. The signal doesn't match thermal emission. It doesn't match the chaotic broadband radiation produced by natural processes like lightning or magnetic reconnection. It matches a modulation pattern. The amplitude varies. Not randomly, rhythmically. The variations occur on timescales of seconds to minutes, too fast to be caused by the object's 7-hour rotation, too structured to be noise. Dr. Mburu applies a spectral decomposition. a mathematical technique that breaks a complex signal into its constituent frequencies, and when the decomposition is complete, a single number emerges. Phi, the golden ratio, 1.618. It's there, encoded in the spacing between the signal's harmonic components. The first harmonic sits at a certain frequency. The second harmonic is 1.618 times higher. The third is 1.618 times higher than the second. The pattern repeats. The ratio is constant. The precision is to 4 decimal places. Dr. Embaru runs the analysis forward and backward. He tests for aliasing, for instrumental artifacts, for mathematical quirks that could produce a false positive. The ratio remains. He writes the report at 0040 UTC. The language is clinical, devoid of emotion. Signal modulation exhibits harmonic structure consistent with the golden ratio, f1.618. Probability of random occurrence, less than 1 in 100,000. The report is shared internally at DXGTL. By 00 UTC, it has been escalated to the directors of all 3 participating observatories. By 10 UTC, it's on the desks of the NASA Administrator, the ESA Director General, and the heads of space agencies in Japan, Canada, and India. By 12 UTC, the news has leaked. The headline is stark: Interstellar Object Emitting Signal with Mathematical Structure. The article, published by The Guardian, cites anonymous sources within the observation teams. It describes the golden ratio. It notes its appearance in art, architecture, biology. It quotes a mathematician. Phi is one of the most recognizable constants in mathematics. If you wanted to signal intelligence, this would be a good choice. The reaction is immediate and polarized. One camp insists the signal is natural, that harmonic structures can arise from resonance phenomena, from the interaction of magnetic fields and plasma, from processes we don't yet fully understand but that require no invocation of intelligence. Another camp points to the accumulation of anomalies, the trajectory deviation, the radar echo, the technetium, the spectral pattern, the angular geometry, the light that doesn't scatter, and now a signal modulated by a mathematical constant. Each anomaly, taken alone, might be explicable, but together, the probability is calculated by a statistician at the University of Cambridge. She considers each anomaly as an independent observation, assigns a conservative probability to each, and multiplies them together. The combined probability that all these features arise by chance, less than 1 in 10 million. She publishes the calculation on her blog. Within hours, it's been cited in dozens of articles, podcasts, videos. The phrase techno-signature is no longer confined to private conversations. It appears in headlines, in press releases, in statements from scientists who have spent their careers searching for evidence of life beyond Earth. Dr. Jill Tarter, a leading figure in the search for extraterrestrial intelligence, is interviewed by National Public Radio. She's cautious, as always. But her words carry weight. We've spent 60 years listening for signals from space. We've built telescopes. We've scanned the sky. We've searched millions of stars. And we've found nothing. Until, possibly now. If this signal is confirmed, and I emphasize if, it would be the most important discovery in human history. The same day, CT Home, a distributed computing project that allows volunteers to analyze radio telescope data on their home computers, announces a special initiative. They're releasing the raw data from the VLA, Meerkat and Arecibo observations to the public. Anyone with a computer can download the data, run the analysis, check the results. Within 24 hours, 10,000 people have joined the effort. Within 48 hours, 50 independent analyses confirm the golden ratio modulation. The scientific consensus remains cautious. The official statements emphasize uncertainty. The word confirmed is avoided. The phrase consistent with is preferred, but the door is open. On April 24th at 16 UTC, a second press briefing is held. This time the tone is different. Dr. Rivas speaks. She's been quiet during the previous briefings, deferring to institutional leaders, but now she's at the podium. Over the past 6 weeks, she begins, we've observed an interstellar object that defies easy categorization. Its motion, its composition, its surface properties, and its radio emissions All exhibit characteristics that are not typical of natural bodies. Some of these characteristics have been replicated across multiple independent observations. Some remain preliminary. We are committed to transparency and to rigorous analysis. She pauses. The room is silent. We do not yet know what we are looking at, but we are looking, and we will continue to look until we have answers. A reporter asks, "Do you believe this is a signal?" Dr. Rivas meets the question directly. "I believe this is data, and the data is telling us something we don't yet understand." The briefing ends. The footage is broadcast globally. The reaction is mixed. Some praise the honesty, others criticize the lack of definitive conclusions. But one thing is clear, the conversation has shifted. This is no longer a story about an unusual comet. This is a story about the possibility, however remote, however contested, that we are not alone, and the clock is still running. 13 days remain before 3i Atlas slips beyond observable range. 13 days to find answers, or to ask better questions. Chapter 11, April 26th. The coma that turned inside out. The observation is made by an amateur astronomer. His name is Takeshi Yamamoto. He's a retired engineer living in Kyoto, Japan. He owns a 25-centimeter Schmidt-Cassegrain telescope mounted on his apartment balcony. He's been following 3i Atlas since the first news reports in March, tracking it across the sky with the patience of someone who watches the cosmos not for career or publication, but for love. On the night of April 25th, he points his telescope toward the coordinates where 3i Atlas should be. The object is faint, nearly at the limit of what his modest instrument can detect. But he's equipped with a sensitive CCD camera, the kind used by amateur astronomers around the world to capture images of asteroids, comets, and distant galaxies. He takes a series of exposures, each 5 minutes long, stacking them to reduce noise and enhance faint details. When he processes the images the next morning, he sees something unexpected. There's a coma, a faint halo of gas surrounding the object. Not unusual for a comet, especially one that's been near the sun. But the coma is moving, not expanding outward, as gas sublimates from the surface and drifts into space, contracting inward. He assumes it's an error, a processing artifact. He reruns the analysis. He compares individual frames. The motion is consistent. The coma, which in earlier images from weeks ago appeared to be spreading away from the object, is now collapsing back toward it. He posts the images on an astronomy forum asking for confirmation. Within hours, other amateur astronomers around the world point their telescopes at the same coordinates. They see the same phenomenon. By April 26th, the observation has reached the professional community. Dr. Zhao requests emergency observing time on the Hubble Space Telescope. The request is granted. Hubble captures a high-resolution image in the ultraviolet, the wavelength where cometary gas glows brightest. The image is unambiguous. The coma is real, and it's contracting. The gas is moving inward at a velocity of approximately 300 meters per second. That's slow on a cosmic scale, but it's measurable, and it's the opposite of what should be happening. Gas expelled from a comet moves away from the nucleus. It's pushed by the pressure of sublimation, by the solar wind, by radiation pressure. There's no natural mechanism that pulls it back, unless something is pulling it. Dr. Sengupta, reviewing the data, proposes a hypothesis: magnetic confinement. If the object has a strong magnetic field, it could trap ionized gas, hold it in place, even draw it inward as the field lines reconfigure. But magnetic fields of that strength require a dynamo, a rotating core of molten metal like the one that generates Earth's magnetic field, or, in smaller bodies, electrical currents flowing through plasma. Neither explanation fits. 3i Atlas is too small, too cold, too inactive to generate a dynamo, and there's no evidence of the plasma needed to carry electrical currents. Another hypothesis: gravitational collapse. Perhaps the object is outgassing, and the gas, instead of escaping into space, is falling back due to the object's gravity. But the mass is too low. The escape velocity from a body the size of 3i Atlas, estimated at roughly 500 meters in diameter, is less than half a meter per second. Gas moving at 300 meters per second would escape easily. The contracting coma defies explanation. And then there's the tail. Every comet has a tail. The gas and dust pushed away from the nucleus by sunlight, streaming millions of kilometers across space, always pointing away from the sun. But on April 26th, the tail of 3i Atlas changes orientation. The shift is subtle, a few degrees, but it's measured by multiple observatories. The tail, which had been aligned anti-sunward, the direction expected from radiation pressure, tilts, it rotates. And then, impossibly, it begins to curve. Tails don't curve unless something is deflecting them. Solar wind can do this, magnetic fields can do this, but the deflection is always predictable, following the streamlines of the solar magnetic field or the trajectory of solar wind particles. This curve is different. It bends in a direction that's not aligned with any known force. Dr. Tanaka, watching the data stream in from observatories on 3 continents, writes in his notes, "Angular momentum change, non-conservative force. Orientation shift suggests active control." He deletes the last sentence, then rewrites it. Orientation shift suggests non-gravitational acceleration. Safer language. But the implication is the same. Something is changing the way 3i Atlas interacts with sunlight, with gas, with the environment around it, and that change is happening now in real time as the world watches. On April 27th, the thermal imaging data from the James Webb adds another layer. The hotspots on the surface, the regions that glow brighter in the infrared, are moving. Not because the object is rotating, but because the emission pattern itself is shifting. Over the course of 6 hours, a hotspot near the equator migrates toward the pole, then fades, then reappears on the opposite hemisphere. It's as if heat is being redistributed, channeled, controlled. Dr. Rivas convenes an emergency meeting of the observation teams. 23 scientists join. The discussion is no longer academic. The tone is urgent. "We're seeing active processes," Dr. Rivas begins. "The coma, the tail, the thermal distribution, these are not passive responses to solar heating. Something is happening on or within this object." Dr. Zhao. "Could it be outgassing? A delayed response to solar heating where volatiles buried beneath the surface are now sublimating?" Dr. Tanaka. "The timing doesn't fit. The object is receding from the sun. Outgassing should be decreasing, not increasing, and it doesn't. Explain the contraction of the coma, Dr. Mbaru. What about the signal? Has the radio emission changed?" A researcher from the VLA responds, "The pulse continues, same period, same modulation, but the amplitude has increased by 8% over the past 48 hours. Silence. 8%, Dr. Rivas repeats. "That's significant?" "Yes, the signal is getting stronger." Another silence. Longer this time. Dr. Sengupta speaks carefully. "If the object is outgassing, if it's shedding material that could create a plasma envelope, and a plasma envelope could act as an antenna, amplifying radio emissions." Dr. Zhao. "Or something inside is transmitting more power." The words hang in the virtual space of the conference call. Dr. Rivas doesn't dismiss them. She doesn't agree. She simply says, "We need continuous monitoring, every available instrument, round-the-clock coverage. If this object is active, we need to document every change." The observation schedule is expanded. The Webb, the Hubble, ground telescopes, radio arrays, all are tasked with tracking 3i Atlas until it fades from view. 11 days remain, and the coma against all logic continues to contract, as if something is waking, as if something is preparing. Chapter 12, May 1st. The Shutdown Directive. The directive is issued at 22 WAST UTC on April 30th. It comes from the Office of the NASA Administrator. 3 paragraphs, marked "For internal distribution only." The key phrase, "All publicly accessible data streams related to interstellar object 3i Atlas are to be temporarily suspended pending comprehensive review and validation. This action is taken to ensure data quality and to prevent premature dissemination of preliminary findings." The implementation is swift. By 23 UTC, the public data portals for the James Webb Space Telescope, the Hubble Space Telescope, and the major ground-based observatories have been updated. The real-time feeds, which had been showing images and spectra as they arrived, are replaced with a message. "Data temporarily unavailable. Scheduled maintenance." The announcement is met with immediate backlash. Within hours, the forums erupt. Social media explodes. The phrase "data embargo" trends globally. Accusations of censorship, of cover-up, of government overreach flood the discourse. Prominent scientists speak out. Dr. Tata from the SETI Institute issues a statement. "Transparency is the foundation of science. If the data is being withheld for validation, That's reasonable, but the timeline and criteria for release must be clearly communicated. Dr. Rivas is more direct. In an interview with Nature, she says, "This decision is a mistake. The data does not belong to NASA. It belongs to humanity. Restricting access undermines trust and fuels exactly the kind of speculation we should be working to counter with facts." NASA responds with a press release on May 1st. The language is diplomatic. The temporary pause in data release is a standard procedure when observations reveal unexpected phenomena that require careful analysis. We anticipate resuming public data access within 7 to 10 days. But the damage is done. The narrative has shifted from scientific curiosity to institutional secrecy. The tone of the news coverage darkens. Opinion pieces question motives. Podcasts dissect the implications. The story is no longer just about 3i Atlas. It's about who controls the information and why. And then the civilian network responds. Within 24 hours of the data embargo, a grassroots coalition of amateur astronomers coordinates its own observation campaign. They call it the Open Sky Initiative. The tools are modest: backyard telescopes, CCD cameras, radio receivers built from hobbyist kits, but the network is vast. Hundreds of observers across 6 continents, and they're not bound by the same restrictions as professional observatories. On May 1st at 18 in UTC, the Open Sky Initiative releases its first public dataset, images of 3i Atlas captured by amateur instruments. Lower resolution than the professional telescopes, noisier but real, and available to anyone with an internet connection. The data shows the object, the contracting coma, the curved tail, and, in the radio observations made by a group of amateur radio enthusiasts in the Netherlands, the pulse at 21.3 centimeters. The pulse is still there, still regular, still modulated. The existence of an independent data stream shifts the conversation. If the government won't provide transparency, the people will. But the civilian network discovers something else. On the night of May the 2nd, a team in Australia detects a change in the radio signal. The pulse, which had been consistent for weeks, stops. At 03:22 UTC, the signal goes silent. For 16 minutes, there's nothing. Just the background hiss of the cosmos, the static of distant galaxies and quasars, and the thermal glow of the universe itself. And then, at 03:38 UTC, the signal returns. But it's different. The pulse is gone. In its place is a continuous emission. Narrow band, modulated, but not periodic, not rhythmic. It's a whisper, a murmur, a stream of information too faint, too complex to decode without sophisticated analysis. The amateur network records it. They don't have the tools to analyze it fully, but they share the raw data. They upload it to public servers. They invite anyone with the skills to examine it, to attempt a decoding, to find meaning in the noise. Within hours, signal processing experts, cryptographers, linguists, and hobbyists begin to work, independently, collaboratively. The effort is chaotic but passionate. One group applies Fourier analysis. They find harmonics, structure, but no clear pattern. Another group tests the signal against known encoding schemes. Binary, hexadecimal, prime sequences, nothing matches. A third group, led by a software engineer in Berlin, applies machine learning. They train an algorithm to identify patterns in the signal to separate structure from noise. The algorithm runs for 12 hours, processing terabytes of data, and it finds something, a repeating sequence, buried in the noise, not obvious, not loud, but present. The sequence is short, 15 elements. The elements are not binary, not simple on-off states. They're amplitude modulations, variations in signal strength that occur in discrete steps. The engineer publishes the sequence on May 3rd. The post is titled Possible Information Structure in 3i Signal. The sequence is analysed by dozens of independent researchers. Theories proliferate. Some suggest it's a primer, a basic introduction to the mathematical or linguistic structure of whoever or whatever is transmitting. Others argue it's an artifact, a product of the signal processing itself. But one researcher, a mathematician at the University of Tokyo, notices something. The sequence, when plotted graphically, resembles a waveform, and the waveform, when analysed spectrally, produces a frequency distribution. That distribution matches, almost exactly, the hydrogen emission profile detected by early radio telescopes in the 1970s. the same profile that was transmitted by the Arecibo radio telescope in 1974 as part of the famous Arecibo message, humanity's first deliberate attempt to send a signal to potential extraterrestrial intelligence. The resemblance is too specific to be coincidental. It's as if the signal is echoing us, reflecting back a pattern that we ourselves sent into space 50 years ago. The findings are shared, replicated, debated, and on May 4th, a new headline appears. Interstellar object may be responding to humanity's own message. The implications are staggering. The speculation is unconstrained. The questions multiply faster than the answers, but the window is narrowing. 7 days remain before 3i Atlas fades beyond the reach of even the most powerful telescopes. 7 days to understand the whisper beyond the static. 7 days to answer the question that is no longer hypothetical. Are we listening to ourselves or to someone else? Chapter 13. May 6th. The faint voice beyond the static. The signal reconstruction takes 3 days. The data is collected from civilian observatories, from the fragmented recordings of amateur radio operators, from the handful of professional facilities that continue to observe 3i Atlas despite the official embargo. The signals are time-stamped, cross-referenced, aligned to account for the position of each observer relative to the object. The process is meticulous. The raw data is noisy, contaminated by terrestrial interference, by solar radio bursts, by the electromagnetic hum of modern civilization. But beneath the noise, the signal persists. On May 6th, a team at the University of Manchester releases the first comprehensive reconstruction. They call it Signal 21.3R, the R for reconstructed. The signal, when cleaned and enhanced, reveals a structure that is undeniable. It's not a simple pulse, it's a modulated carrier wave. The carrier frequency is 1.42 GHz, the hydrogen line. But the modulation, the information encoded on top of the carrier, is complex. The modulation contains a harmonic envelope. The harmonics are spaced according to integer multiples of a fundamental frequency. But the spacing is not uniform. It follows a pattern. And that pattern matches, almost exactly, the spectral profile of the Arecibo message transmitted from Earth in 1974. The Arecibo message was a brief radio transmission, 3 minutes long, aimed at the globular cluster M13, 25,000 light-years away. It contained information about humanity, our numbers, our location, our chemistry, our place in the solar system. It was never intended as a practical communication attempt. The round-trip time would be 50,000 years. It was symbolic, a demonstration of what we could do, a message in a bottle cast into the cosmic ocean. But the signal from 3i Atlas echoes its structure. Not perfectly, not identically, but close enough that the similarity cannot be dismissed. Dr. Emberu, who's been tracking the radio emissions since the first detection in March, reviews the reconstruction. He's exhausted. He hasn't slept more than 4 hours a night in weeks. But when he sees the harmonic match, he feels something he hasn't felt in a long time. Or, he writes in his log, the signal is not random. It is structured, and the structure references a transmission that we made. The probability that this is coincidence approaches 0. He doesn't write the next sentence, but he thinks it. Something heard us, and it answered. The reconstruction is shared within the scientific community on May 6th. By evening, it's public. The team at Manchester uploads the data to an open-access server. They publish a preprint with the title, Harmonic Analysis of Radio Emission from 3i Atlas, Evidence for Structured Communication. The paper is cautious. It does not claim proof of extraterrestrial intelligence. It does not use the word message, but it presents the data. It quantifies the match, and it concludes, the observed signal structure is consistent with a response to the 1974 Arecibo transmission. Alternative explanations involving natural phenomena have not been identified. The reaction is immediate. News outlets around the world lead with the story. Interstellar object may be sending message. Scientist detects signal matching human broadcast from 1974. Are we receiving a reply from space? The headlines are breathless. The tone shifts from skepticism to possibility, from caution to hope. Dr. Tata gives another interview. This time, her words are measured but unequivocal. For 60 years, SETI has searched for a signal from space. We've looked at millions of stars. We've listened for patterns, for structure, for anything that might indicate intelligence. And now, in the radio emissions from an object that has travelled between the stars, we may have found what we've been searching for. She pauses, then adds, but we must remain cautious. Extraordinary claims require extraordinary evidence. The signal is consistent with the response. It is not yet proof. The scientific community remains divided. One group argues that the match is real but does not necessarily imply intelligence. Resonance phenomena, they suggest, could produce harmonic structures that happen to resemble the Arecibo transmission. Coincidences, however improbable, do occur. Another group points to the accumulation of evidence, the trajectory deviation, the radar echo, the technetium, the spectral pattern, the light that doesn't scatter, the contracting coma, the curved tail, and now a signal that echoes a transmission we made 50 years ago. Each piece, taken alone, might be explained away, but together they form a pattern, and patterns are what intelligence creates. Dr. Zhao, speaking at a hastily convened symposium at Caltech on May 7th, offers a perspective that resonates widely. Science is about following the data wherever it leads, and the data is leading us to a conclusion that many of us are uncomfortable with, not because the evidence is weak, but because the implications are profound. We are trained to look for natural explanations, but we are also trained to recognize when the natural explanations no longer fit. She pauses, then continues, I don't know what 3i Atlas is. I don't know if it's a probe, a derelict, a beacon, or something we don't have words for, but I know it's not a comet, and I think it's time we stopped pretending otherwise. The comment is controversial. Some colleagues applaud her honesty, others criticize her for jumping to conclusions. But the speech is widely shared. It becomes a touchstone for those who believe the evidence is sufficient to warrant a shift in the conversation. Meanwhile, the object continues to recede. The distance is now 32 million kilometers. The signal is weakening. The Webb and Hubble are operating at the edge of their capabilities. Ground telescopes struggle to track the faint point of light against the background of stars. On May 7th, the narrow band emission changes again. The continuous whisper, which has persisted for 5 days, fragments. It breaks into discrete bursts. Each burst lasts approximately 3 seconds. The bursts are separated by silence. The timing of the burst is analysed. The intervals are not random. They follow a sequence. 1, 1, 2, 3, 5, 8, 13. The Fibonacci sequence. The same mathematical pattern that appeared in the spectral emission observed weeks earlier. The same sequence that Matteo Rees identified in the spacing of spectral peaks. It's repeating. Across different datasets, across different types of observations, the pattern is consistent, and it's unmistakable. On May 8th, at 12 UTC, NASA lifts the data embargo. A statement is released. In the interest of transparency and in recognition of the global interest in the study of 3i Atlas, NASA is resuming public access to all observational data. We encourage the international scientific community to engage with this data and contribute to the ongoing analysis. The statement does not explain the original embargo. It does not apologize. It simply moves forward. The data floods back online. The real-time feeds are restored. The images, the spectra, the radio recordings, all available again. And the world watches, because the window is closing. 5 days remain. 5 days before 3i Atlas slips beyond observable range. Before the geometry of orbits, the limits of technology, and the vastness of space conspire to end the conversation. 5 days to listen, to understand, to answer. Chapter 14. May 10th. First glimpse after the sun. The final image arrives at 0814 UTC on May 10th. It is a composite, a mosaic assembled from observations made by the James Webb Space Telescope, the Hubble Space Telescope, and the combined light of ground-based observatories in Chile, Hawaii, and the Canary Islands. The data spans wavelengths from ultraviolet to mid-infrared, capturing facets of the object that no single instrument could reveal alone. The processing takes 4 hours. Teams at NASA Goddard, ESA's Operations Center in Darmstadt, and the Space Telescope Science Institute in Baltimore work in parallel, aligning the images, calibrating the colors, enhancing the faint features at the edge of detectability. At 12:31 UTC, the image is released. and humanity sees 3 Atlas clearly for the first time. The shape is not natural. The conclusion is inescapable. The object is elongated, roughly cylindrical, with a length estimated at 700 meters and a width of approximately 150 meters. The proportions are unusual, a length-to-width ratio of nearly 5:1. Most asteroids are irregular, their shapes sculpted by collisions and fractures. Most comets are rounded, smoothed by sublimation and thermal cycling. But 3I Atlas is angular, faceted. The surface is divided into geometric sections, each reflecting light differently. Some sections are dark, absorbing nearly all incident sunlight. Others are brilliant, mirror-bright, flashing as the object rotates. The facets are not random. They follow a pattern, a lattice, a structure that suggests purpose, and there's more. Near one end of the object, the bow, as some researchers begin to call it, there's a protrusion, a delicate branching structure that extends perhaps 50 meters from the main body. The branches are thin, almost gossamer, visible only in the highest resolution images. It looks like an antenna, or a sail, or something in between. Near the opposite end, the stern, there's a concentration of the hotspots observed in the infrared. The thermal emission is strongest here, suggesting heat generation, or retention, or redistribution. The image is analysed pixel by pixel, every feature is catalogued, every anomaly is noted. Dr. Rivas, viewing the image for the first time, is silent for a long moment. Then she says quietly, "It's beautiful." Dr. Zhao, standing beside her in the operations room at Caltech, nods. It is, and it's not ours. The image is released to the public at 14:02 UTC. The press briefing that accompanies it is brief. Dr. Leone speaks for NASA. He describes the observation strategy, the processing methods, the collaborative effort that produced the composite. He does not speculate. He does not use the word artifact. He simply presents the image and invites the world to see what the telescopes have seen. The reaction is immediate and overwhelming. The image is shared millions of times within the first hour. It appears on every news platform, every website, every screen. People stop in the streets to look at their phones. Conversations pause. The world, for a moment, focuses on a single question. What are we looking at? The forums, the social media platforms, the comment sections, all overflow with theories, speculation, emotion. Some see confirmation of what they've believed for years, that we are not alone. Others see ambiguity, a puzzle that demands more data, more analysis, more time. Scientists weigh in. Experts from fields as diverse as aerospace engineering, material science, planetary geology, and archaeology offer perspectives. An aerospace engineer notes that the length-to-width ratio is consistent with designs optimized for travel through interstellar space. Long and narrow to minimize collisions with interstellar dust. A material scientist points out that the reflective facets could be thermal control surfaces, designed to radiate heat in specific directions, to maintain a stable internal temperature despite the harsh environment of space. A planetary geologist argues that crystalline structures, formed in low-gravity environments, can produce angular, faceted shapes without invoking artificial construction. An archaeologist, in a moment of levity that goes viral, quips, "If this is natural, it's the most architecturally ambitious comet I've ever seen." But beneath the humour, the speculation, the cautious analyses and bold declarations, there's a shared sense of wonder, and uncertainty, and humility. Because the truth is, no one knows. The data is clear, the image is unambiguous, but the explanation, the definitive answer that science demands, remains elusive. On May 11th, the signal changes for the last time. The Fibonacci bursts, which had persisted for 3 days, cease. The narrowband emission fades, and then, briefly, the original pulse returns. The 3-hour, 12-minute rhythm. The modulation at the hydrogen line. It pulses once, twice, 3 times, and then it stops. The silence is noted by observatories around the world. The VLA, Meerkat, Arecibo all confirm. The signal is gone. Dr. Mbaru, who has been monitoring the radio emissions continuously for 6 weeks, writes in his final log entry, "Signal ceased at 22:47 UTC on May 11th. Cause unknown. Object continues to recede. Distance now 35 million kilometers. Further observation unlikely to yield additional data." The object is fading. The brightness has dropped to magnitude 28. Too faint for all but the largest telescopes, and even those are struggling. The integration times required to capture usable images are measured in hours. The signal-to-noise ratio is dropping. On May 12th, the observation campaign officially concludes. The Webb and Hubble are released to pursue other targets. The ground telescopes resume their scheduled programs. The data is archived, the reports are written, the papers are submitted, and 3i Atlas continues its journey. Outbound, away from the Sun, away from Earth, into the dark spaces between stars. In the weeks that follow, the analysis continues. Researchers refine their models. The trajectory is computed with increasing precision, tracing the object's path backward into the galaxy's past and forward into its future. The origin remains uncertain. The best estimates suggest the object came from the direction of the constellation Lyra, perhaps ejected from a star system hundreds of light years away, millions of years ago. The destination is equally uncertain. In another million years it will pass near another star, or perhaps not. The trajectory is sensitive to gravitational perturbations, to forces we cannot measure, to the chaotic dynamics of a galaxy in motion. It came, it passed, it departed, and in its wake it left questions. Questions about the nature of interstellar space, about the processes that eject objects from distant star systems, about the chemistry of worlds we cannot visit, and questions about ourselves, about our place in the cosmos, about whether the signals we send into the void are heard and answered. The scientific consensus, such as it is, remains cautious. The anomalies are acknowledged, the patterns are confirmed, but the leap from unusual to artificial is one that most are not yet willing to make, not without more data, not without replication, not without the kind of certainty that science demands. But there are voices, growing in number, growing in confidence, that argue the evidence is sufficient, that the accumulation of improbable coincidences crosses a threshold, that the signal, the structure, the geometry, the chemistry, all point to a conclusion that is uncomfortable but unavoidable. Dr. Rivas, in a lecture given at the International Astronautical Congress in October 2025, offers a reflection. 3i, Atlas challenged us. It challenged our models, our methods, our assumptions. It forced us to ask questions we weren't prepared to answer. And it reminded us that the universe is not obligated to be simple, or familiar, or comprehensible on our terms. She pauses, then adds, maybe it was never built to speak. Maybe it was only built to be seen. And maybe that's enough. The lecture is watched by millions. The phrase built to be seen becomes a refrain in the discussions that follow. Built by whom? For what purpose? The questions linger. And on cold, clear nights, when the sky is dark and the stars are bright, people look up and they wonder, because somewhere out there, moving through the silence, through the vast and empty dark, an object is travelling, crystalline, faceted, angular. Maybe it's a comet with chemistry we don't understand. Maybe it's a relic of stellar evolution we've never observed before. Maybe it's a natural process, strange and wondrous, shaped by forces that operate in the cold between stars. Or maybe it's something else. Maybe it's a glimpse, a message, a reminder that the cosmos is vast, that the unknown is infinite, and that we, on our small blue world, are part of a story far larger than we can yet imagine. The window has closed, but the conversation has just begun. This is not science fiction. This is May 2025, where sunlight fades and mysteries wake. This is beyond the solar veil. The question that remains. 6 months later, in November 2025, a secondary analysis is published in the Astrophysical Journal. The paper, authored by a consortium of 47 researchers from 18 countries, presents a statistical meta-analysis of all the anomalies observed in 3i Atlas. The conclusion is carefully worded. The collective probability that the observed features arise from natural processes is less than 1 in 100 million. While this does not constitute definitive proof of artificial origin, it warrants consideration of technosignature hypotheses alongside natural explanations. The paper is peer-reviewed, it is debated, it is cited hundreds of times within the first month, and it shifts the conversation. The phrase technosignature hypothesis is no longer fringe, it is mainstream, It is on the table. It is a possibility that science is willing to consider. Meanwhile, in the private sector, plans are underway. SpaceX, after months of speculation and denial, confirms that a sensor payload was deployed during the April Starship XL mission. The payload, they reveal, was placed on a trajectory that brought it within 3 million kilometers of 3i Atlas in late April. The data from that flyby, radar scans, high-resolution imaging, spectrographic analysis, is still being processed. But preliminary results, shared in a closed-door briefing with NASA and ESA, reportedly show features that were not visible from Earth-based observations. The details are not made public. But the fact that the mission occurred, that private industry crossed the gap, that humans reached out to touch, however briefly, an object from beyond our solar system is historic, and it's just the beginning. By 2026, proposals are circulating for follow-up missions, not to 3i Atlas, which is now too distant, but to the next interstellar visitor. Because there will be a next one. Statistics suggest that at least one interstellar object passes through the inner solar system every year. Most are too faint, too fast, too far to detect. But we're learning. We're building better telescopes. We're watching the sky more carefully. And when the next visitor arrives, we'll be ready. In the meantime, the world moves on. The headlines fade. The conversation shifts to other mysteries, other discoveries, other crises. But the image remains. The composite of 3i Atlas, crystalline, faceted, angular, beautiful. It's printed in textbooks, displayed in museums, shared in classrooms. It becomes an icon, a symbol of a moment when humanity looked outward and saw something that defied explanation. And in the quiet moments, in the stillness of the night, the question lingers. Was it built, or did it grow? Was it a message, or a mirror? We don't know, not yet. But for the first time in history, we have a reason to ask, and that perhaps is the most important discovery of all.